Now let's discuss partitioning and data locality in DSE Graph. In case you'd like more information on this subject, you can always read my blog post from the DataStax Academy website titled Understanding Graph Locality. Let's first introduce the concept of graph partitioning. For those who are familiar with DSE, you'll understand partitioning in the terms of Apache Cassandra. That is, Apache Cassandra stores data in partitions. We have partition keys. One of the main tricks to achieving those low millisecond P99s at scale with Apache Cassandra is to set up your data model properly around a good partition access pattern. For graphs, partitioning means something slightly different. With graphs, partitioning refers to how one groups vertices and edges of a whole graph into specific sections called subgraphs. This is done for performance, analytics reasons, security, or data management purposes. Here you'll see an example of a graph being partitioned into 3 different subgraphs. The trick of graph partitioning is to balance graph access patterns, write patterns, and data size constraints. Like most things in distributed architecture, we're talking about trade-offs. Theoretically, graph partitioning is an incredibly hard problem. This is because of the complexities involved from highly connected components. There is no magic algorithm that can generate optimal graph partitions for you. For the best results, you have to consider each individual use case and be creative. In DSE Graph, we can actually combine the concepts of partitions in both Apache Cassandra and graph theory to come up with practical implementation choices to solve real-world, at-scale graph challenges. This is because of the way DSE Graph projects the graph model onto Cassandra. In this diagram, we're looking at an oversimplified example to illustrate the concept of how graph partitioning is applied to Cassandra and DSE Graph. You can see in this diagram, each colored subgraph maps to each partitioning schema within Cassandra. In this example, we see 3 different subgraphs represented by 3 different colors. And we see how those subgraphs map onto Cassandra by the groupings of partitions using the same colors on the right. You can control partitioning in DSE Graph by carefully choosing vertex labels and Vertex ID design. This is very similar to those working with the Cassandra components of DSE. Choosing vertex labels, especially in the presence of entity type hierarchies, can affect graph partitioning in DSE Graph. Underneath the cover, DSE Graph creates 2 Cassandra tables for each vertex label or type that is created. These Cassandra tables use a primary key that corresponds to the vertex identifier. This means that vertex property and edge data is always stored together on a node. And we can use Cassandra's wide row partition and clustering keys to further control data placement in DSE Graph. Data placement is the central implementation concept of graph partitioning. In DSE Graph, this technique is named User-Defined Vertex IDs. It's worth mentioning in older versions of DSE Graph used to generate IDs for users. This, it turns out, resulted in suboptimal data placement and impacts a graph's ability to scale. Using User-Defined Vertex IDs is a recommended approach for working with graphs in DSE Graph. We have 3 types of User-Defined Vertex IDs. The first is a Vertex ID based on a simple partitioning key structure. This is the most basic implementation in which every new vertex is created using unique Cassandra partitions. Cassandra will hash the partition key and store the data randomly throughout the cluster. This is the easiest method of implementation that ensures an even distribution of your data across your cluster. But this also doesn't provide users with any control over data placement or locality. In other words, this is the most simplistic approach to graph partitioning. You could even say this is a graph without partitioning. The next user-defined vertex type is to use composite partition keys. This means that instead of just using one property to identify a unique vertex, 2 or more properties are used to identify a unique vertex. The results of this approach are very similar to the simple partition key approach we described on the previous slide. The only difference is, here we can use more than one property key to identify our partitioning. The final user-defined vertex ID type is a vertex ID using partition and clustering keys. This method provides the most control over graph partitioning and enables graph users to achieve data locality by using the same partition key property to identify multiple vertices that belong to the same subgraph. This is the most powerful design pattern as it allows multiple vertices to reside in the same physical partition and share the same node. Here you can see that we have two vertices with a partition key of Alice in Wonderland. It would be very efficient to retrieve all movies with a given title by simply traversing on the partition key only. DSE Graph will translate these operations to Cassandra partition access patterns, which are very efficient. Okay, so you now see how we can use the power of Cassandra's wide row data model to achieve a practical solution to graph partitioning. Give this exercise a go and we'll be right here when you're ready to learn more about DSE Graph.